Over the last 100 years, buildings have got taller and taller as more and more people have tried to get onto the same piece of land. But towers have long been a feature of cities for all sorts of reasons. To look more closely, for example, at this medieval Tuscan town is to discover an oddity. 1 or 2 towers for the church and the town hall might be expected, but the people of San Gimignano built over 70.
Le grandi famiglie della città che litigavano continuamente, volevano soverchiarsi l'une con le altre, volevano costruire torri sempre più alte per manifestare anche pubblicamente la loro potenza. Il comune stabilì con una legge precisa che la torre più alta doveva essere quella del comune. Le quali torri però non hanno un significato veramente reale, hanno un significato soprattutto simbolico.
San Gimignano may seem just a curious medieval relic, a reminder of a time when people could afford to construct buildings like these simply as status symbols. In a modern city of towers, like New York, you'd expect the motives for building tall to be more hard-headed, but are they? Today, one young New York developer wants to build the world's tallest building on this site. Millions of dollars are at risk in a development that New York doesn't really need. Why is he so determined to do it?
It's an extraordinary cost, but yeah, I believe it's going to happen. I've just always felt that New York City has had the tallest building, and now we don't. Chicago does. And you go to Chicago and you see signs, "Welcome to Chicago, home of the world's tallest building." The fact is that this is an opportunity. I don't say it's the end all, but it's an opportunity for New York City to get something that it doesn't currently have and that it always has had. And I believe that we'll be successful in doing that.
There's a few people in New York City that think that they have a divine right, I guess, to build everything to ever be built from this point forth in the city. And more power to them. I think it's really a tough job. They're going to build everything, but, you know, perhaps they can.
Mr. Trump wants to build a taller building now, but Mr. Trump has wanted to do a lot of things that he hasn't been able to do. Yes, I think people will try to build a taller building, and they probably will. Frankly, I think the only ones that can afford it now are the Russians, because they don't have to make a building pay.
I don't think whether it's the tallest building in the world or the tallest building in Philadelphia, the tallest building in Frankfurt, or the tallest building in Timbuktu, I don't think it actually really makes all this much difference. I think where it probably makes more difference is that the media grab more attention if it's of a greater height.
On a personal side, I think there's a competition among developers and/or builders to have the biggest and the best and the tallest. And you can see it because a lot of people accept or assume the title of the tallest when a lot of times that isn't true. You've seen people add stories to their buildings and use various excuses like the height of the floors or the number of the elevator cars or something. That's a macho type of thing. People always want to be the biggest and the best.
Without thinking of phallic symbols or anything like that, yeah, I guess so. They're prettier than short, fat ones. They're more fun to look at. Tall girls are better than short, fat girls to look at, so.
What constitutes a skyscraper? That's a skyscraper. The Tribune Tower qualifies as a skyscraper for me because it seeks the heaven much in the way the Tower of Babel is said to have done. It's a building that gets smaller, that culminates and terminates not in an artificial, clipped-off way. So for me, it's an uncircumcised version of a tall building. That's the circumcised version, which is a building which is clipped off, which doesn't seek the heaven. It's practical, it's pragmatic, it's repetitious, it's capitalist. It's based on entrepreneurial speculation. My use of the metaphor circumcised or uncircumcised really has to do with clipping something off at the top as opposed to a natural way that it peters out, to use the metaphor inadvertently, okay?
Whatever Chicago's skyscrapers may look like, it's the structure on the inside that's important. Skyscraper engineering began in Chicago just over 100 years ago. One October night in 1870, a fire broke out in a barn, a fire that was to spread over the entire city in 48 hours, destroying about a third of the property. The wooden buildings went first, but the so-called fireproof cast iron buildings didn't do much better. In the heat of 3,000 degrees, iron columns melted to liquid metal and set fire to nearby buildings. The fire had provided an unexpected opportunity to try new techniques for building upwards. Within days, a massive rebuilding operation began. Up till then, most buildings had been constructed by piling one stone or brick upon another. This building marked the end of an era. It was the tallest masonry building ever constructed, 16 stories high.
In Chicago in the 19th century, we got in a building like the Monadnock building, we would again have our spread footings. In this case, we would probably have some kind of caisson or piling. We're then building very tall masonry walls, and those masonry walls, again, are wider down at the bottom. In the case of the Monadnock, they're about over 6 feet wide down at the bottom. We're putting in intermediate floors, and the Monadnock, I believe, is about 12. And then there are also intermediate columns in the center that have, up until now, had very little to do with the stability of the overall structure. The structure really was made stable because of the weight of the exterior masonry walls.
With stone and brick buildings, the walls have to be thick enough at the base to support the weight of the entire building above them. The 6-foot thick walls on the lower floors meant that the people in these offices had to put up with less light and smaller rooms than those who worked higher up. But when the owners decided to extend onto an adjacent site, they used a new building material, steel, instead of masonry, to support this second structure.
Somewhat earlier than 1900, we get to the development of the steel frame. Here we have a whole new situation, because now we still have our spread footing, our pile foundation, but we're building a very thin structure out of steel. There's no exterior wall at all to begin with. We are putting in a system of floors, and all that we're doing is setting on each floor a little bit of what looks like a masonry wall, but it's actually very thin, and it's supported entirely by the structure that was there before. We could actually begin putting the brick on that building, starting at the top and working down.
This somewhat dumpy building has the distinction of being the first true skyscraper, a tall building in which the weight of the walls and floors is supported entirely by a steel framework. Steel is produced by removing carbon from iron ore in a furnace. At that time, it had only been available in quantity in the United States for about 20 years. Unlike iron, steel wouldn't snap if it was bent or stretched, so it could be used in vertical columns and horizontal beams to carry safely the expected loads on a building. This new technology, born of Chicago's need to build quickly, was now taken up in New York, where the financial district pushed its way to the water's edge. In the 30 years from 1876, the city skyline was transformed. In the Wall Street area, church towers were now dwarfed by dozens of buildings rising to 20 and 30 stories as part of New York's commercial expansion. But that was just the beginning. It was a time when many companies were amalgamating, bringing all their workers into the big city under one roof. The bigger companies competed fiercely for building space in the same square mile, with convenient access to colleagues, competitors, and gossip. New York was on the brink of an immense transition. This elegant 19th century city was about to be taken over by the skyscraper in a fanfare of 20th century excitement. The skyscraper was also to intrigue artists and photographers who tried to capture its romantic side in impressionistic street scenes. This was New York's most famous skyscraper when it was built in 1902. Its distinctive shape, designed to fit into a rather awkward junction, gave it the name of the Flatiron Building. The pointed end is only 6 feet wide, and it rises nearly 300 feet to the 21st story. But the increased heights made possible by steel frames created a problem. No one could be expected to walk more than half a dozen flights of stairs. So yet another new technology was needed, the passenger elevator. Industrial lifts had been around for a long time, but they were unsafe. When Elisha Otis dramatically demonstrated his new safety elevator and installed it in this New York department store, he was developing a technology that was to be crucial to the next 100 years of building high. Those customers adventurous enough to try the new method of transport were hoisted gracefully up 5 floors at a speed of just half a mile an hour. And the complications of powering the device meant that the journey could be an eventful experience.
If you can visualize, this is the way it was 130 years ago when you stepped into the first Otis passenger elevator, I should say. The cab was somewhat like this. This is probably not the original cab. The gate didn't exist at that time. The operation wasn't with this so-called car switch. It was more like pulling a rope. You had to pull the rope up to go down or down to go up. The interesting part about it, the rope had a ball on the end of it. When the car got to the top, the ball hit a little plug on the top of the car and stopped the elevator automatically. The attendant probably was dressed in a beautiful uniform. People sat down, perhaps. The ride was very, very slow, and but it was something. It was an elevator. It was transportation. The elevator was driven by a series of belts and pulleys from a central steam engine. The same steam engine used to run the fans in the building, the pumps in the building. Also at that time, the development of the hydraulic machines. The hydraulic machines were the pistons, pumped water into a piston, just like a jack in the garage. And the elevator came up, and as you pull the rope and let the water out, the elevator went down. However, the hydraulic elevator had a big disadvantage in that when you got to a floor, it was very difficult to control. The elevator stopped at the floor. So as a consequence, the operator had a hand-wheel brake that he used to, when he opened the doors, turn the brake, clamp the elevator on the rails, let people go in and out, release the brake, run to the next floor, put the brake on, which was extremely awkward and it's time-consuming. The electric elevator solved many of those problems.
Without a piston as big as the lift shaft, the new drum elevators meant that buildings could go virtually as high as the cable would stretch. The Singer Building was a new world's tallest at 600 feet and 47 stories. And people going about their daily activities could see it from all over New York. There now began a competitive boom in skyscraper building as architects, developers and corporations got a taste for height. The Woolworth Building became a tourist attraction from the day it opened. The terracotta walls were really just a thin coating on the modern steel skeleton underneath. but in outward style, the building pretended to be a Gothic cathedral, erected to the glory of Mr. F.W. Woolworth and his nickel and dime stores. As competition for office space grew, the extravagant designs of earlier years gave way to crude commercialism. A notorious building that changed skyscraper design was an office block built by an insurance company, the Equitable, in 1915. This building made good commercial use of the site by cramming in 1 million square feet of rentable floor space. But it destroyed the character of the area. Because it rose vertically from the pavement, people complained bitterly about the loss of light. They found themselves walking through dark, gloomy canyons. So the city authorities acted. They brought in regulations to ensure that buildings were set back as they rose from the street to let in light and air. These drawings, predicting the effect of the regulations on future skyscraper designs, proved to be uncannily accurate. The first building following the new zoning regulations had all the key features of a new generation of skyscrapers. After a lull in the 20s, the race for height took off again with the Chrysler Building, which opened to tenants in 1930. Now that buildings had to be stepped back as they went higher, slender towers were in vogue, and none was more admired than this celebration of the Chrysler Automobile Company. The walls were studded with Chrysler hubcaps. When this building was under construction, its architect was desperate for the title of the world's tallest building. To his dismay, another skyscraper on Wall Street was completing construction at about the same time. Its architect had added a flagpole so as to be 2 feet taller than the Chrysler. At the last moment, in great secrecy, the Chrysler workers assembled a 123-foot spire inside the building and raised it through the roof to claim the coveted title. Architects and developers had clearly abandoned all pretense that skyscrapers were simply office buildings. For William Van Allen, the Chrysler architect, this triumphant act was just one rather dotty gesture in a decade of skyscraper madness. At the 1931 Beaux-Arts Ball, New York's leading architects arrived dressed up as their own buildings. Skyscrapers had begun to take on personalities with lives of their own. One artist has shown the Chrysler Building after gracefully giving up her honor to the Empire State Building. It seemed perfectly natural to skyscraper enthusiasts to celebrate yet another world's tallest building by using an airship to deliver a bundle of newspapers to the 102nd story. The Empire State Building was to be 1,250 feet tall, and it had a special place in the affections of New Yorkers from the day it was announced. Every step of the construction was recorded on film. The building was to weigh 365,000 tons, at that time by far the heaviest skyscraper ever built. On the island of Manhattan, there's no danger of any weight, however heavy, sinking into the ground. The solid rock goes down for miles. For the designers of the building, the main force they were worried about was gravity, the immense downward pull on all the materials in the building that had to be resisted by the steel structure. Each connection had dozens of bolts or rivets, and because all the calculations of stress and load had to be done by hand, it was difficult for engineers to be sure they'd anticipated every weakness. No one wanted to risk a failure, and so they consciously built in excess strength. As the building rose, it became a daily focus of attention.
Well, in those days, when I was 18, I guess I was full of vinegar. And well, anyway, there was 2 girls. I lived on Willis Avenue in the Bronx. And there were 2 beautiful girls who worked for Saks. And they lived on Willis Avenue on 37th Street, if I remember. And they came to work, they had to be to work at 9 o'clock. Of course, I was at work at 8 o'clock in the morning. So the girls started. I don't know what floor it was, I really don't remember. But I would go out and wave to them, you know. And then the next floor, we did a floor a day, and it got higher and higher and higher. And finally, the girls would, would be out there at 5 of 9 or 10 of 9 looking up like that. And there'd be, all you have to do in New York is look up, and there'd be 30, 40 people looking up, waving to me.
As the steel rose, whole armies of craftsmen followed the steelworkers. The building contained an immense amount of limestone and granite, fixed to the frame by hundreds of stonemasons. And while concrete floors were being poured on the higher levels, plasterers and electricians were already at work on the floors below. It was mass production on a huge scale. The site was active for 24 hours a day. 3,500 workers were hired, and 14 lost their lives in various accidents. In a steel frame like this, the most important connections are riveted in all three directions, up, down and sideways, so that the whole framework is stiff enough as it rises further and further from its fixed base. The building went up at extraordinary speed, under pressure from the financiers, who didn't want their money to be tied up for more than 18 months. The steel girders arrived on the site within 3 days of the molten steel being poured out of a furnace 400 miles away. "65,000 people a day were to work in the completed building. They needed all the working conditions they had been used to nearer the ground: heat, lighting and plumbing, and most important of all, fresh air. But at this stage, regulating the airflow in a tall building was still a primitive business.
So buildings such as the Woolworth Building, which is a 1910 era, and even the Empire State Building, which is around 1930, and the Chrysler Building, which is the early 30s, still had no air conditioning. The only means they had to use to get comfortable was to open up the windows. So that if you look at these buildings, there is generally about a 20 to 30 foot space maximum between the window and the core, so that you always were in fairly close proximity to a window, and you opened up the window, and that's how you got cool. But with the advent of air conditioning, we could cool spaces inside a building, in the core of a building, and that enabled building floor plates, which means the distance from the core out to the window could be much greater than 30 feet. So we could have a 100-foot distance between the elevator where you get off and the windows. So the interior space is a space that has lights and people and desks just like the exterior space. But the heat that is in that space from lights and people and office equipment and little personal computers has to be absorbed 365 days a year, whether it's wintertime or summertime.
In some ways, a skyscraper is like a chimney. As the warm air inside rises to the top, it creates a suction at the bottom, which could suck in a gale of cold air.
Everybody's been through a revolving door, but very few people think about really why they have revolving doors. And when you think about a leaf-type door, your normal 7-foot high by 3-foot wide door, you open up the door and you walk in. You are making a large opening into the lobby of the building that air can rush in along with you when you go into the lobby. So the revolving door was invented so that you can go into the revolving door, and if you look, you have the weather stripping around the edge of the door. You go into 1/4 of the door, the little cubicle, and as you rotate the door around, only that little cubage of air that is with you when you're 1/4 of that revolving door enters into the lobby with you, the revolving door maintaining a seal against the outside, so that we can keep the outside air from rushing in to the base of the building and then rushing up the elevator shafts and the stairway.
The skyscrapers of the 30s and 40s were the last really heavy buildings. After the Second World War, materials were scarce and expensive. Engineers had to build lighter buildings, and this raised a new problem: the force of the wind.
The wind forces are the predominating force that we have to deal with in the design of the building. A wind wants to make the building overturn or roll over or bend or lean, and we have to analyze the structure and design it so that it doesn't lean or bend and that it serves its useful purpose. And that's almost the same thing that happens to a boat. If you take the example of my sailboat, which is a 37-foot sailboat, the mast is a compression element. It's a pipe. It's made out of aluminum, but it's not stable by itself. And it's supported by a series of stays or shrouds or guys. And these are wires, they're cables, they're like ropes. And they take tension very well, but when they get compressed, they go limp, like a piece of string. What happens when the wind blows on a sailboat is that the boat wants to heel, lean, very similar to what happens with a building.
Fortunately, the foundations of buildings are more solid than water.
What we're really trying to do is to keep this building from drifting sideways. And I think what that building is trying to do when the wind blows from the side is to sort of collapse in this fashion. And so each one of those little rectangles within the building, within the